Hello, welcome to Basics of Finite Element Analysis. Today is the 7th week, second day of this course, and what we will do today in this particular lecture is a continuation of our discussion on shear deformable beams or Timoshenko beams. And in the last lecture what we had done was we had developed weak formulations for the two equilibrium equations. These weak forms are expressed here on your screen, and as a follow up to this, what we will start looking at are the boundary terms of these equations and interpret these boundary terms in terms of what do they mean. So, what we will look at are the boundary terms at this point of time. Okay. So, we will look at, our aim is to figure out what are the essential boundary conditions and also what are the natural boundary conditions for such a beam. So, when we look at equation 1, this is equation 1, okay. And when we look, we see that the weight function is W1, weight function is W1, and in equation 2, the weight function is W2. Okay. The coefficient of weight function in the first equation is GAKS times psi plus dW over dx. And we had discussed earlier in one of our lectures that the coefficient of the weight function constitutes the natural boundary condition. So, this is the thing which is the natural boundary condition associated with the first equation. And physically, what does it represent? Psi plus dW over dx, we had explained earlier, is nothing but shear strain, right. That is what we had explained in the last class. When I multiply this shear strain by G, then it becomes shear stress. And if I have a beam and the shear stress here is tau, and suppose I multiply this by that area of the cross section of the beam, then that shear stress times area is nothing but shear force. So, in the first equation, this term represents physically, it represents the shear force. Okay. Now, the other thing we had discussed was that this, in earlier class also, that this is essentially minimum potential energy statement, the same thing for the second thing also. So, when I multiply V by a displacement, that corresponds to work done by the system. So, this W1, if I replace it by W, which is the displacement, then the essential boundary condition associated with the first equation is displacement, and the natural boundary condition associated with the first equation is the shear force. And when I multiply W by V, I get the work done. Okay. Next, what we will do is we will look at the second weak form, which is equation 2. So, in equation 2, in the boundary term, which is here, I have W2 is the weight function. The coefficient of that W2 is EI d psi over dx. And this, so what is psi? Psi is rotation. Psi is rotation of the original vertical line AB with respect to it, how much it rotates by, right, that is the rotation. And if I differentiate it once again, I essentially get the curvature, right. And when I multiply that curvature by EI d psi over dx when I or d2w over dx square in for Euler-Bernoulli beams, that times EI is the moment. So, this is our bending moment, and because this equation also represents minima of potential energy. So, I have to multiply moment with the angle or the rotation. So, W2 corresponds to psi, which is the rotation. So, in the second boundary equilibrium equation, the essential boundary condition is rotation and the natural boundary condition is moment. So, either I specify in the second differential equation rotation at a given end point or the moment, and in the same sense, if I am dealing with equation 1, either I have to specify the displacement, which is W, or I have to specify the shear force. So, this is how we interpret these terms in context of the boundary conditions, okay, and what are the variables. So, next what we do is we look at these terms and we define these, represent these in terms of Qs, because in our FE formulation on the right side of the equality sign we always represent something as F plus Q. Okay. So, that is what we will express these terms as. So, we will write Q1E, that is for the eth element, is equal to minus GAKS psi plus dW over dx, and this thing I am evaluating at x is equal to 0. So, I am evaluating this term which is underlined in red. When you evaluate it at 0 and its negative value, that is Q1. Q2, we do the same thing, but to the term in the second differential equation. Okay. So, this is just a question of nomenclature. So, Q2 equals minus EI d psi over dx, and this thing is evaluated at x is equal to 0. Then Q3 for the eth element is not a negative sign, but a positive sign, and this entire expression GAKS psi plus dW over dx, x is evaluated at HE, and Q4 is positive of EI d psi over dx evaluated x is equal to HE. So, using this terminology or nomenclature, in the first equation I have Q1 and Q3, and in the second equation I have, in the second equation I get Q2 and Q4. So, once again, in the first equation I have Q1 and Q3 as the boundary terms, in the second equation I have Q2 and Q4 as the boundary terms. And then we have also seen what are the definitions of our essential as well as natural boundary conditions. So, with all this information, now what we will do as a next step is once again rewrite our these equations, equations 1 and equation 1 and 2 in terms of Qs also. So, we will replace these boundary terms by Qs. So, that is what we get. So, what we are doing is updated weak form. So, 0 to HE dW1 over dx GAKS psi plus dW over dx, and now I am moving the force term to the right side. So, it is 0 to HE weight function 1 times f times dx plus weight function evaluated at location 0 times q1e plus weight function, the first weight function evaluated at location he times q3e. Okay. So, this is my equation 1, and the second equation when I put in q's is partial differential of W2 with respect to x. Oh, so I forgot, everywhere I should have x bar. So, dW2 over dx times EI d psi over dx plus 0 to he W2 GAKS psi plus dW over dx bar equals weight function, second weight function evaluated at 0 times q2e plus second weight function evaluated at he times q4e. This is my E2. Okay. So, these are the two equations, and at this stage we are almost ready to introduce interpolation functions, because we have created a weak form for both the differential equations, we have extracted the boundary terms which are q's, and at this stage we can replace psi and w by respective interpolation functions like we did in the earlier case. Now, couple of points which I would like to make at this point of time. First, w and psi, they are independent variables, they do not depend on each other. So, when I select interpolation functions, then these interpolation functions have to be mutually independent. Okay. So, this is one thing. So, in traditional, so I have to have one set of interpolation functions multiplied by some constants for w, another set of interpolation functions for psi. They cannot be identical. That is one thing. Second thing is, what we see here is that to have we have the highest derivative of psi is d psi over dx. So, psi has to be at least linear in nature, so that its derivative exists. We do not have a second order derivative. So, any element which has at least a linear variation of psi, that is the type of function we have to choose. Second thing is w. So, in case of w also, the highest order derivative in these equations is dw over dx. So, w should also be at least linear in nature. So, that is there. The third thing is that there is no rule at this point of time which says that the order of w and order of psi should be same. Psi could be a linear function and w could be quadratic. The mathematics at this stage does not restrict us to impose conditions where psi and w, they have to be of the same order. So, based on all this understanding, and we have seen that psi has to be continuous, it has to be a unique thing, and the nature of psi is same as the nature of u, which we had seen in case of heat conduction or bar equation. So, essentially what I am trying to say is that at this stage the Lagrangian interpolation functions which we had developed earlier will work in this case. Okay. So, for an Euler-Bernoulli beam, Lagrangian interpolation functions do not work, because at every node we have 2 degrees of freedom, right. Here also we have 2 degrees of freedom at every node, but they are expressed through 2 different functions. So, in case of Euler-Bernoulli beam, we had developed hermetic functions because W was same, but we had to extract 2 independent degrees of freedom from here. But here we have 2 independent functions psi and W, so Lagrangian functions work. So, we express W and psi as so W is a function of x bar, and that equals j equals 1 to m some constants wje times interpolation functions, and here we call this interpolation function as alpha. Okay. And similarly, psi is a function of x, and that is equal to j is equal to 1 to n, because there is no rule which says that the order of psi and order of w they should be same. Okay. And this equals some constants Sj times beta j, and beta is the interpolation function, and all this is for the eth element, Now, if m is equal to 1, if m equals 1, then w is constant over the element. If m equals 2, then w is a linear interpolation function, right. If m equals 3, then w is quadratic. Same thing is true for psi also. If n is equal to 1, then it is constant, n equals 2, then it is linear, and so on and so forth. So, now at this stage we have to make a choice. So, at this stage we choose m equals n equals 2, just to make our life simple, and we have to go from here somewhere. So, we have to choose some values of m and n, and we are just choosing that m and n are same and they are equal to 2. So, let us call these equations as equations 3. So, if that is the case, then dw over dx bar m is equal to 2. So, w is w1 times alpha 1 plus w2 times alpha 2, right. So, if that is the case, then dw over dx is w1 d alpha 1 over dx bar plus w2 d alpha 2 over dx bar. Okay. And earlier, in our earlier classes, we have seen that a linear function over an element can be expressed as alpha 1 is equal to x bar over he, and alpha 2 is equal to 1 minus x bar over he. We have developed these functions. So, we do not have to reinvent the wheel. So, if that is the case, then dw over dx equals, if I differentiate, I get w2 minus w1 over he. Okay. So, dw over dx is difference in w's, w2 minus w1 over he. So, we call it 4a. Also, let us look at rotation. So, rotation equals S1, and I have called them as betas, and okay, actually I will fine. So, this is equals beta 1 plus S2 beta 2. Okay. and beta 1 and beta 2 they depend on x, they change with x. So, they depend on x, S1 and S2 are constant, beta 1 and beta 2 are functions of x. Okay. Now, we know that for thin beams, we had seen that in the case of the thick beam there is a shear deformation, but in thin beams the shear deformation is not there. So, the planes which are normal initially they still remain normal, and if that is the case, then what is our shear strain? We had said the shear strain is psi plus dw over dx, and if the planes normal planes still remain normal, which means shear strains are 0, which means psi plus dw over dx is equal to 0, and this is for thin beams. Which means psi equals minus dw over dx. Okay. So, if that is the case, then for thin beams, and again once again beta 1 is equal to x bar over he and beta 2 is equal to 1 minus x bar over he, right. So, for thin beams psi equals S1 x bar over he plus S2 1 minus x bar over he, and this equals minus of dw over dx, and dw over dx is the thing which is underlined in red. Okay. So, this one is equal to W1 minus W2 over he. Now, these two sides, so what you see is that the right side is a constant and the left side depends on x. The left side depends on x and the right side is independent of x. This can be true only if the coefficient of x on the left side is 0. So, what is the coefficient of x? So, this can be true only if coefficient of x on LHS is 0, only then it will be independent of x. So, that will be there when S1 minus S2 is equal to 0. This is the coefficient of x, okay, which means S1 equals S2. So, what this means is that for thin beams S1, which is a constant, should be same as S2. S1 is the constant and it is multiplied by this beta 1, S2 is a constant which is multiplied by beta 2, and they have to be same. Okay. Now, if S1 is equal to S2, if S1 is equal to S1 is same as S2, what does that mean? Suppose you have an element, and if I am going to plot in the y direction the rotation psi, then psi will be constant over the element, right, because S1 is the coefficient at first node, S2 is the coefficient at second node, the values at both these nodes are same and it is a linear element. This means that psi is equal to constant, and this is S1, this is S2, this is node 1, this is node 2. Understood? If psi is constant, then d psi over dx will be 0. So, for thin beams, if we are doing all this process and we are choosing that m is equal to n is equal to 2, and if we do all this process, ultimately what all that means is that in a thin beam d psi over dx will be using this formulation, it will come out as 0. If it comes out as 0, then we go back and look at our equation. We look at this term, this is the equation in, we look at this equation, second equation, and we see that here this term E di over dx, E times d psi over dx, this will be 0, and this term is essentially related to the bending energy of the beam. It is related to the bending energy of the beam. So, which means that the beam has very little bending energy, which is not the reality, because when you are bending a beam, a lot of energy is spent, right. So, this formulation creates a problem because of this numerical problem. It is not a real problem. When we bend the beam, it is bending and it takes some energy, but this problem, the way we have formulated, it creates this problem because it forces psi to become constant over the element, which causes the energy related to bending vanish in the equilibrium in the weak formulation, and this problem is known as shear locking. It is known as shear locking, okay, and it is known as shear locking, and the reason for this is that psi, because of all our assumptions, it comes as constant at the end of the day over the domain of the element. So, to solve this, to avoid this numerical problem, so this is a numerical problem. To avoid this numerical problem, we take two methods, and we will discuss about these two approaches in our next lecture. So, all what we have discussed in today's lecture is the cause of shear locking, which causes this bending energy term to vanish, because the way we have formulated, it forces psi to become constant over the element, and to avoid this, we have to adopt some methods, and what we do about those methods is something we will discuss in our next class. Thank you.